Hi, this is Mrs. LaBarbera. This is Physics Chapter 12, Sound and Light, Video 5. Today's topic is Snell's law. The objectives are know Snell's law, be able to calculate angle of incidence, angle of refraction, or index of refraction for one of the two mediums. Be able to select sketch diagrams of refracted rays as they pass between two or more mediums. Be able to use diagrams to determine relative speeds of a medium based on the direction of rays. The general relationship governs the refraction of light as it passes from one medium to another of different optical density is known as Snell's law. The relationship is n1 over n2 equals sine theta 2 over sine theta 1. Rewritten that equation, you'll have n1 sine theta 1 equals n2 sine theta 2. The first equation on the left basically states the index of refraction is inversely related to the angle of refraction. So the bigger the index, the smaller the angle. So angle theta 1, theta 2 are the angles of incidence and the refraction respectively, and n1 and n2 are the absolute indices of incidence and the refractive media respectively. So if theta 1 is 0, that means the wave goes straight down, then theta 2 will be 0. So that means the light will not change directions. So Snell's law can be rearranged with this way: sine theta 1 over sine theta 2 equals to n2 over n1. The ratio n2 over n1 is called the relative index of refraction for the two media. So here is a Snell's law with a diagram. Incident ray, we usually call that medium where the incident ray enters is medium 1 and goes into the refracted another medium that's called a medium 2. So in medium 2 there are three variables: n2, lambda 2, v2, and theta r actually. So there's four things. And for medium 1 there is incident angle, reflected angle. Also, you have n1, lambda 1, and v1. So here, this line is called a boundary. So Snell's law says n1 over n2 is sine theta 2 over sine theta 1. They're inversely related. So this equation, remember we also taught when we talked about absolute index of refraction, we said n1 and the lambda 1 are inversely related. That means when you multiply them together, that gives you a constant. So n1 lambda 1 equals to n2 lambda 2. n1 times v1 also equals to n2 times v2. The bigger the index, the slower the speed. The bigger the index, the smaller the wavelength. So that's the relationships. Let's take a look at our first example. So a ray of monochromatic light of frequency 5.09 times 10 to the 14 Hertz is traveling from water into medium X. The angle of incidence in water is 45 degrees, and the angle of refraction in medium X is 29 degrees. Calculate absolute index of refraction of medium X. So here tells you the frequency of the light is 5.09 times 10 to the 14 Hertz. You don't really need this for calculation. Basically, this 5.09 times 10 to the 14 Hertz is the frequency of a yellow light. And that is index of refraction in the reference table. So all the index are given to us is about this yellow light. So we just need to know whenever we're given this number, that means we can use reference table to find index of refraction. You don't actually need to use this for calculations, because in this case frequency doesn't change from one medium to another medium. We know speed and wavelength changes, not frequency. So this is Snell's law problem. You write down the medium n1 and n2. n1 is the angle of incidence, so that's the media, and n2, the medium, is the refraction medium. So n1 sine theta 1 equals to n2 sine theta 2. In this case, n1 is water, theta 1 is 45 degrees. Theta 2 is 29 degrees. We have to find N2. So N2 is N1 sine theta 1 divided by sine theta 2. After you plug everything in, you have 1.94. That is N2. That's the absolute index of refraction of medium X. Another example, a ray of light in air is approaching to a layer of crown glass at an angle 42 degrees. Determine the angle of refraction of light ray upon entering the crown glass and upon leaving the crown glass. So this one didn't give us the frequency. You can just assume the frequency is yellow light. So it's from air, that's your N1. N2 is your crown glass. Let's calculate this two first, the boundary number 1. So N1 sine theta 1 equals N2 sine theta 2. In this case, you're trying to find sine theta 2. Once you find sine theta 2 up, after you substitute everything in, you'll have to do inverse sine. And then you should have 26 degrees right over here. The next question is, what is the ray coming out? Now here, if you have this part as N2, then this part has to be N1. So again, it doesn't really matter which one is N1, which one is N2. You just have to match the angle. So N2, this would be your theta 2, this blue one. And N1, this is your theta 1. So in this case, you're trying to find the angle coming out. In my, the way I did it, I have this theta r as a theta 1. So I have sine theta 1 equals N2 sine theta 2 divided by N1. And N2 is 1.52 sine 26 degrees, and 1 is 1. So that's air. So I have 0.666, and again, theta 1 is inverse sine of this number, gives you 42 degrees. Look, 42 degrees, you enter 42 degrees. So see the boundary, this is rectangular prism. Whatever the angle you come in is the same as the angle goes out. It doesn't really matter how many mediums in here. You can have a crown glass, you can have diamond, you can have all different water, and whatever comes in, the angle is the angle you go out. Okay, that's an important concept. So upon entering, the light bends toward normal, because from less dense to denser, one coming out, it bends away from normal, but these two angles are always the same. So when the light approaches a layer which has the shape of a parallelogram that is bounded on both sides by the same material, then the angle at which the light enters the material is equal to the angle at which light exits layer. Refraction, there are some special cases. We already know when light rays enter another medium at a 0 degree angle, when the angle of incidence is 0 or the light is perpendicular to the boundary, then there is no bending. Another occasion when it doesn't bend is two medium have the same index of refraction, even though they are different materials, such as corn oil and glycerol. These two, as you can see from the reference table, they are both 1.47. So for the light wave cannot see the difference, because light wave is only concerned about index of refraction. So the angle theta 1 and equals to theta 2, the light will just go straight. Let's take a look at another example. A ray of light with frequency 5.09, here we go again, times 10 to the 14 hertz, moves from air into flint glass. The angle with which the ray strikes the surface of the flint is 40 degrees away from normal. Which is the faster medium? Determine the angle of refraction and draw the refracted ray. So the angle of incidence is always the angle between incident angle and the normal. So over here, it has to be 40 degrees. We know air is less dense, so the speed in air is faster because it has a lower index. How do we find the angle of refraction? Use Snell's law, and 1 sine theta 1 equals N2 sine theta 2. So the top air is N1, and on the bottom flint glass is N2, so we can find theta 2 equals 23 degrees. Determine angle of refraction, that's angle of refraction. Draw the refracted ray from this point and moving away. So the angle has to be 23 degrees with a normal. Remember, all rays must have arrows because that's indicate the direction of waves travel. Whoops. Okay, another example. When a ray of light is traveling in water reaches a boundary with air, part of the light ray is reflected and part is refracted. Which ray diagram best represents the path of reflected and refracted ray? So let's take a look. All reflected ray must have the same angle as that's a law of reflection. A, B, C are correct. D is wrong because reflected angle does not equals to incident angle. So we know it's definitely not D. Next one, refracted ray has to bend in a certain way. This is from water to air. Since air is less dense and water is denser, so you are going to bend away from normal. So this is toward normal, this is away from normal, this one is away from normal, but on the wrong side. Remember, the refracted ray and incident ray has to be on the opposite side of the normal. So the answer is B in this case. That's it for today. Thanks for watching.